The event horizon is often described as the point of no return, a cosmic boundary. It's not a wall or a solid surface, but a threshold. Cross it and escape becomes impossible. Not even light, the fastest thing in the universe, can break free. But what lies beyond it? What happens to the matter, the light, the information, as it falls inward, pulled into a darkness so complete that even time itself begins to behave strangely? This is where science becomes less certain and more imaginative. We know what happens outside the event horizon. We can measure, model, and observe the effects. But inside, we can only speculate. And that speculation opens a doorway to some of the most mind-bending ideas in physics. According to Einstein's general theory of relativity, once an object passes the event horizon, it continues to fall. Not through space, but through time. Inside the black hole, all paths lead to a single point, the singularity. The singularity is the theoretical core of a black hole, a place of infinite density, a place where the known laws of physics break down. But here's the catch. Infinite doesn't mean we understand it. It actually means we don't. It's a placeholder, a red flag in the math that says, we need a better theory here. Some physicists believe the singularity doesn't even exist in the way we imagine, that our theories, pushed to their limits, are just showing us the edge of their usefulness. And so, questions arise. Does time stop at the singularity? Does matter become infinitely compressed? Or does it transform into something we can't yet describe? One radical idea is that the matter doesn't vanish or stay trapped, but instead emerges elsewhere, in a different region of space, or even a different universe. This is the basis of the white hole hypothesis, the theoretical reverse of a black hole, where matter only comes out but never goes in. It's speculative. There's no observational evidence for white holes, but the mathematics doesn't forbid them. Another possibility: what falls into a black hole is not destroyed, but stored, somehow encoded on the event horizon itself, a concept called the holographic principle. This principle suggests that all the information about what falls into a black hole isn't lost, but smeared across its surface in a kind of cosmic record, as though the three-dimensional reality we experience inside the event horizon is just a projection of that surface. It's an elegant idea, and it could help solve one of the most famous puzzles in physics: the black hole information paradox. This paradox was first brought to light by Stephen Hawking in the 1970s. He proposed that black holes emit radiation, now called Hawking radiation, and that over time they lose mass and eventually evaporate entirely. But if they evaporate, what happens to the information about what fell in? In classical physics, information can't be destroyed. But Hawking radiation, as we understand it, carries no trace of the matter's original properties. It's like burning a book and being unable to recover the story from the ashes. This troubled physicists for decades. If information is truly lost, then our understanding of physics, of determinism and quantum mechanics, needs a major revision. But if it's not lost, where does it go? Some suggest it's preserved in the quantum entanglement of particles. Others believe it's stored at the boundary of the black hole, again, that holographic surface. And some theories, wild, beautiful, and difficult, suggest that black holes are not destroyers, but bridges. Bridges to other parts of the cosmos, or even to entirely separate universes. This is the realm of wormholes, hypothetical tunnels through space-time, connecting distant points via shortcuts through higher dimensions. Could black holes be one end of a wormhole? Could the singularity, instead of being a point of destruction, be a gateway? We don't know, and we may never know, because crossing the event horizon seals the fate of whatever enters. We can't see inside. We can't send a probe and receive data back. All we have are the clues, the behavior of matter just outside, the equations of general relativity, the whispers of Hawking radiation. But even without certainty, black holes offer us something rare. They give us a place in the universe where mystery is preserved, where not knowing isn't a failure but a frontier. They are the most extreme laboratories in existence, natural crucibles for testing the boundaries of our theories. They remind us that science is not just about answers. It's about questions that remain open, that stretch our imagination, that connect physics with philosophy. Because to ask what happens beyond the event horizon is to ask about the nature of reality itself. And tonight, as we drift in thought or fade into sleep, we carry that question, not to conquer it, but to marvel at its depth. After all, some mysteries aren't meant to be solved. They're meant to be felt.